Hello. Today I'm going to try something old, but in a really new way. Let's talk about this. So, I'd like to explain the types of plasmas that there are out there to you as if they were sports cars. So, hello, my name is Greg Friedman. On this channel, I like to talk about science, frequently specifically focused on electric discharges because that is my specialty. And a couple of days ago, I got a really cool question. I would love a review of all the different types of plasma, in particular how to delineate them based on what they are and what they are not. If we were to treat all plasma subtypes like we were analyzing a sports car, understanding the nuance between them, such as the engine, fuel management, transmission, cooling features, functions, etc., it would help me better understand, one, what plasma is generally speaking, and two, what separates all different kinds of plasmas and why they are different, including cold plasma. Very cool question. At first, I was just going to make a short video, but I really love the analogy with sports cars. You know, in the United States, especially, I think, more so than in other countries, people are really into cars, especially in suburban America. So everybody, including young kids, understands the difference between the cars and what makes a car cool and what makes a car fast. So I think talking about plasma, explaining plasma to undergraduates, or even sometimes I give lectures to high school students, I think it's a really, really good way to connect with the audience and explain fairly complex physical phenomena in a really simple way that people would actually retain. So I went down that rabbit hole and made a whole presentation about it. So let's dive right into it. Understanding plasma in the sports car framework. So we're going to take a deep dive into what plasmas are, what they're not, why the differences matter, and we'll tie all of that into sports cars. So what is plasma? Well, so you have solid. Let's take a block of ice. And you can give energy to that block of ice. How do you do that? You can put it on a frying pan. You can shine a laser at it. You can explode a thermonuclear bomb next to it. You can compress it. Regardless of how you give it energy, and molecules start moving faster, so the whole thing becomes fluid. You continue giving it energy, and the thing becomes gas. You continue giving it energy, you start stripping electrons from atoms, creating positive ions and free electrons, and that soup of electric charges, electrons, partially ionized molecules, that soup is called plasma. It's ionized gas and lots of charges floating around, so it responds well to electric fields, to magnetic fields. And the defining feature of the whole thing is ionization, not just the energy you put into it. So not just temperature, and temperature is just one of the degrees of freedom. There are 4 temperatures, if you will. They are vibrational, rotational, translational, and electronic degree of freedom, and all of those in physics are measured in electron volt and considered to be all temperatures. So there are 4 temperatures. But anyway, so what's our spec sheet for our race mobile? Well, with a sports car, you have engine size, just how big the engine is. What is the equivalent in plasma? Well, the overall temperature. So the higher the temperature, the more power your engine has. Now, there is difference between electron temperature and ion temperature, and in colder plasmas, that matters. In hotter plasmas, both of those are the same. So temperature is your engine size. Now, the energy source is the type of fuel you are putting in your car. So you can have electric fields. Your source of energy could be lasers, heat, radio frequency wave, radiation, you name it. Your transmission is degree of ionization. So what is the percentage of your gas that is ionized? That kind of sets the gears of your system. Now, the cooling system of your sports car, the plasma equivalent of that is what's called collisionality. It's how many collisions per unit time, how many interactions between atoms, electrons, and molecules happen in a given moment of time. Now, weight and power ratio of your vehicle, well, that's density. It's just gas density. So how many atoms, molecules, and charges we have per cubic centimeter. And equilibrium or non-equilibrium state of your discharge corresponds to the best equivalent I could come up with is track, not street legal race car, and a street legal race car. Let's dive right in. Thermal plasma, hot plasma. Usually the temperature is in the order of 10 to 6 to 10 to 8 Kelvin. That's 1,000,000 to 100 million Kelvin, or roughly 2 million to 200 million Fahrenheit, give or take. It is very hot. Thermal plasmas, classic thermal plasmas, are basically completely 100% ionized. Everything, all the atoms are fully stripped, not fully, but to some extent stripped of electrons that are available for stripping. And the plasma is in local thermodynamic equilibrium. So if you look at spot, each spot will be in thermal equilibrium. Now this is basically the most powerful plasma, just like a V12, brute force. Everything is in balance. The car is super powerful. What would you find such a plasma? Gosh, it's fusion plasmas at the core of the tokamak reactor. At the core, at the very center of a lightning during the moment of strike. Also, you find this inside of stars. So this is the light that we have during the day is coming from thermal plasma inside of our main star. So this is pure performance. It's powerful and not very practical at human scale. Maybe tokamak reactors for a fraction of a second we can have this craziness, but usually this is reserved for stars. Cold plasma, think of it as a Tesla or, hybrid vehicle. It's non-equilibrium plasma. It's very, your electrons are very fast, high energy, 10 to 100,000 Kelvin, but they have very small mass, so they can't really move on collision. They can't really move bigger ions, so they can't increase temperature. So the temperature, as you know it, is room temperature, so you can touch these plasmas, and yet they're very energetic and they're very tunable. In this context, the word cold plasma is frequently misused. It's kind of like a marketing term. Plasma is out of thermal equilibrium. It's not a purely thermal plasma, so it's a non-equilibrium plasma. And when thermal plasmas in thermal equilibrium are called hot, so naturally these plasmas, the out of equilibrium ones, are called cold. Cold doesn't always mean cold. It can be down to room temperature. It can be up to a few thousand Kelvin. You can still have a so-called cold discharge even at those relatively elevated temperatures. And examples of these plasmas are dielectric barrier discharges, plasma jets, radio frequency microwave plasmas. So there are plenty of those in the lab. And cold plasmas are typically what you would find in the lab. They are easier to produce, and far less dangerous than purely thermal plasmas. Now, another thing to look at is weakly or strongly ionized plasmas. So kind of like street legal sports car. Weakly ionized plasma is not enough ionization to be the super powerful V12 racetrack only. But it still can do some speed. So weakly ionized plasmas is what most plasmas you will find in the industry are. They're highly reactive. They're chemically very useful for different kinds of processes. And weakly ionized does not mean it's weak or useless. It means it's not 100% ionized. It's not fully ionized. And these are terms that come to us from physics. So a lot of physics is done with a pencil and a piece of paper, and names like fully ionized, strongly ionized, weakly ionized, those are all terms that define states the plasma is in. But when you're working with that plasma in a lab, it can still do a lot of good, or it can do a lot of bad. And you'll find weakly ionized plasmas. A good example is fluorescent lights, neon signs. Plasma TVs are weakly ionized plasmas. And as I mentioned, most lab and industry plasmas are this kind of plasma. Fully ionized plasmas are the thermal plasmas I mentioned. Your ionization degree is close to 100%. Your temperature is on the order of tens of millions of Kelvin, or 20s of millions of Fahrenheit if you prefer that. And these plasmas are largely governed by electromagnetic processes, so you can control them. Moving charges have magnetic field, so you can control them with a magnetic field, and they respond to electric field, so you can do magnetic confinement. You can do a lot of stuff that researchers around the world are using to create internal confinement fusion or create fusion in tokamak reactors. So these fully ionized plasmas are what's promising us near-free electricity in the hopefully near future. Now there is another type of plasma, is dense plasmas versus diffuse plasmas. They can have same power output, but completely different handling. With a car example, dense plasmas are like welding torch. You have rather high density of your discharge. It's maybe at high pressure, so atmospheric pressure is considered high pressure for plasma physics. Or you can have diffuse plasmas, low pressure plasmas, long paths, so distance between molecules is big. You have low pressure situation. Solar winds, ionosphere, aurora are naturally occurring examples, and some lab scale plasmas are diffuse because they're low pressure. A lot of processes in plasmas are done at low pressure to preserve uniformity of your surface modification. Another very interesting example of plasmas is dusty plasmas. Dusty plasmas is any kind of plasma with dust particles in it. Either you're trying to grow those dust particles for, making all sorts of different new materials, or you're trying to get rid of those dust particles because you're in semiconductor manufacturing and you want ultra high purity silicon chips. And dusty plasmas are very interesting for lots of scientific research applications, including those in space when gravity doesn't matter anymore. When you're in space, dusty plasmas can offer very interesting, for example, you can study Coulomb interactions between nanoparticles on almost a macro scale. It's very, very interesting, cool stuff, and I'm happy to take a deep dive into dusty plasmas. I did a lot of my early research, and my master's thesis is basically on a form of dusty plasmas where dust is micron and submicron size water droplets. And that was done for biological applications for very uniform printing using plasmas. The next type of plasmas are magnetized and unmagnetized plasmas. And with car example, it's all-wheel drive versus rear-wheel drive. It's magnetized plasmas is something you would find, for example, in tokamak, where you're using magnetic field to compress flowing plasma to keep it away from the walls so it doesn't destroy the walls and compresses to the center, trying to raise the temperature to that close of the sun so you can have fusion reactions start. Unmagnetized plasmas are basically lab scale plasmas where magnetic fields aren't applied to control plasma, not just lab scale, like early universe plasma, where universe was expanding. There was no strong influence of magnetic field and everything was expanding outwards, minding its own. Anyway, so those are the types of plasmas. Let's talk about some myths. What these plasmas are not. Cold plasma does not mean it's low energy. It means that ions are at room temperature or maybe a little bit above, but not in thermal equilibrium with electrons. That's what cold plasma means. It can still be quite powerful. Plasma is not just hot gas. It's because it's ionized, it responds to electric and magnetic fields. It can be relatively easily controlled, and it has a lot more going for it than just temperature. Weakly ionized plasmas does not mean they're weak. Means they're not fully ionized. So most of plasmas that are employed in the industry today, arguably almost all of them are weakly ionized plasmas. Does not mean they're weak. No, it doesn't. All plasma glows. Not at all necessarily. Everything depends on everything. Most plasmas that you will see, they glow, but there are a lot of plasmas, it's without emission in human visible light spectrum. A lot of plasmas are used to generate deep ultraviolet that you're not going to see, but the silicon wafer chip would, or the mask that's on a silicon wafer chip, or I should say the photopolymerizable material under the mask on the silicon wafer chip. Anyway, so not all plasmas produce light. That is not a requirement. And some of the very interesting plasmas, including so-called dark discharges, don't produce light, but they can still do a lot of interesting chemical processes and otherwise. And another myth is plasmas are exotic and rare. Nah, about 99% of stuff you see in a telescope is plasma. What is, I always found that example to be heartwarming. Oxygen is not the rarest thing in a galaxy. Diamonds, gold, nope. Wood. Wood is one of the rarest things in a galaxy because as far as we know, this is the only planet that can produce wood. Plasmas are everywhere. Wood is rare, especially Pennsylvania black walnut is my favorite. Anyway, so what are some applications? What is each model of the sports car? Yeah, there are a bunch of sports cars. But what is each one built for? Like, there are things that a Lamborghini should not be used for, like racing it on the beach. So there are different specializations for both race cars and plasmas. Hot plasmas, fusion energy, tokamaks, astrophysics, a lot of modeling involves thermal plasma modeling because that's what stars made out of. Material processing, extreme temperature analysis, like you use hot plasmas in a lab to simulate reentry and test new materials for SpaceX. Cold plasma, very popular these days in medical and biomedical applications for wound healing, cancer treatment, that kind of stuff. In agriculture and food safety, so this is my whole CAN plasma series, is mostly focused on applications of cold plasmas. You have surface sterilization, water sterilization, air cleaning, all of that. Weakly ionized plasmas are arguably, in my separation here, are weaker than cold plasmas, and they're typically used for fluorescent lighting, neon signs, LEDs are arguably plasmas. We can happy to have a separate chat on whether I think LEDs are plasmas or not. Semiconductor etching and deposition, some display panels, so it's weakly ionized plasmas. Magnetized plasmas, fusion confinement, tokamaks. Ion thrusters, so you're using effects of magnetic field to accelerate ions out of plasma to push the spacecraft forward. There's a lot of research in magnetic reconnection. To dusty plasmas, well, planetary science, so I told you 99% of the known universe is plasma, and there's a lot of dust around there, so how plasma interacts with various sized dust in the galaxy and space is very important, both for bigger and smaller plasmas and bigger and smaller dust. In very interesting, fascinating application, you can use dusty plasmas for synthesis of novel materials, frequently very cool novel materials. And fully ionized plasmas, they're inside of the fusion reactor, in interior of the stars and in internal confinement fusions. So those are very interesting applications of fully ionized plasmas. So kind of in summary, we talked about hot plasmas, thermal plasmas, cold plasmas, weakly ionized plasmas, fully ionized plasmas, dense and diffuse plasmas, dusty plasmas, and magnetized plasmas. And they're all sports cars. They're just different, one from the other. And unifying thread between cars and plasmas, and why I really like the viewer's question, is cars in general, four wheels, engine, some kind of a seat, and a steering wheel. Yeah, all cars are the same. Car enthusiasts would disagree with you, right? So first of all, not all cars are the same. Plasma is the fourth state of matter, so all plasma is the same. Oh, heck no. Same as sports cars. Their prices vary dramatically. They're same family, wildly different builds. Sports cars and plasmas. Your price can be very little to very high. I think I can buy a car for, let's say, $10,000. And I can also buy a car for $10 million. So your difference in price can vary by many orders of magnitude. Same with plasmas. Some plasmas are a few bucks. Some plasmas are a few million bucks. Ionization and electromagnetic behavior, they also unify cars and plasmas, because with cars you have lots of levers, how you can control the car. You can steer it, you can accelerate, you can decelerate. I guess that's about it. But you can also change the form of the car to change it. So there are a lot of unifying specs between sports cars and plasmas. Temperature alone does not define plasma. Neither does how fast the car can go. Doesn't make, you can't classify sports cars by their top speed. You also need to look at what terrain they can travel on and things like that, and whether they can swim or not. I don't know if there are any sports cars that are also amphibious vehicles, but that would be cool if there were. They have to be. There's got to be. And interestingly, when you think of cars are engineering marvels, right? They're, every car nerd I know considers himself an engineering nerd at the same time. Well, dude, let me tell you, plasmas are arguably one of the most engineerable. I don't know if I invented that word, but a plasma and car is most engineerable state of matter for plasma and vehicle for the car. And you're surrounded by it. Both of those. You're surrounded by cars. They're everywhere. They're out of my window this way. They're out of my window that way, that way, that way. And that way, those are called airplanes. And that way, those are called tunnel diggers. Cars are everywhere, so are plasmas. So I think this was a really fantastic question. Thank you so much for asking. I created a presentation out of it. I'll confess, it wasn't just for you. I will now use this presentation in my presentations to undergrads and high school students to try to raise their interest in plasma. If you have pointers and tips for me, leave them down in the comments section. I would love to read and think about your comments. And if you have any questions, especially if they start with can plasma, I would love to answer them. Thank you. Peace. I'll see you in the next one.